All right, guys, we're going to jump in and look at the second part of Chapter B, Chapter 8, Part B of Chapter 8. And we're going to learn about types of formulas, and we're going to do something called a combustion analysis. So we're going to talk about those things. Let's go ahead and jump in. Last week we talked about experimental error, percent yield. Let's talk this week about some different types of formulas. So one type of formula is what we call an empirical formula, and that's a formula that shows the simplest ratio of elements present in a compound. We also have what's called a molecular formula, and that is a formula that shows the actual number of each element in a compound. So in some situations, we are determining the exact number of atoms that exist in a molecule. That's what we call a molecular formula. That's this one up here. Okay, so a couple of molecular formulas would be something like H2O2. In one molecule of hydrogen peroxide, we know we have two hydrogen atoms, and two oxygen atoms. Another molecular formula is C3H15N3. And that molecule, that is the exact number of atoms that exist in that molecule. And then one more example would be H2O. In water, in one molecule of water, there are two hydrogen atoms and one oxygen atom. Okay, these are all molecular formulas. Okay, now it turns out that sometimes we can write this in a way that we say the ratio of one element to another. That would be our empirical formula. And you can kind of think of this kind of like you think of a reduced fraction, right? That's kind of the idea behind it. It's just the ratio of one to another. So if we look an example of something that would be an empirical formula is for, if we were looking at what we have up here with H2O2, our empirical formula for that would be HO. And what we see is that for every one H, there's one O. If you look at the next formula below that, that's C3H15N3, our empirical formula for that would be CH5N. And that means for every one C, we've got 5 H's and 1 N. Another empirical formula is the formula for a carbohydrate, which is CH2O. That is these are all empirical formulas. They tell us the ratios. Okay. Now, none of these empirical formulas here are exact formulas. You don't see any this is carbohydrates, right? This is the empirical formula for a carbohydrate. Oops. But you don't ever see a carbohydrate with that molecular formula. There are several, I think you talked about this in your book, some of the molecular formulas for carbohydrates are C3H6, let's fix that, C3H6O3, another one is C5H10O5, you have to excuse my handwriting here, and C6H12O6. These are all molecular formulas for carbohydrates. Now, I have a question for you. Can a formula be both a molecular formula and an empirical formula? Sure. Something like H2O. This gives the simplest ratio, but it is also the exact formula. So just because something is in a reduced form does not mean that it cannot be a molecular formula. We simply know that if something is not in a reduced, it can't be an empirical formula. We simply just know that if they're in this form up here where they can be reduced, right, we know that they certainly are not empirical formulas. Oops, put my O back. Okay, I now want to talk to you about how molar mass can relate two molecular formulas and empirical formulas, okay? And we're going to use that carbohydrate CH2O formula, okay? That's our empirical formula for a carbohydrate. Okay, now, suppose you were told, this is the empirical formula, and you were told that the molar mass is 150.15 grams. Well, I can figure out what the mass of the empirical formula is, right? For this particular, oops, I'm going to get rid of that. For this particular empirical formula, we know that we would have 12.01 for the carbon, 2.02 for the hydrogen, two of those, and then 16.00 for the oxygen. Well, when I add all that up, I get 30.03 grams, okay? That is the mass of the empirical formula. Okay, that's the mass of the empirical formula. This is the molar mass, which would be the mass of the molecular formula. That would be the mass of the whole molecule, correct? So if I know that the mass of the whole molecule is 150 grams, what I can do is I can take that and I can divide it by the mass of my empirical formula and see what the ratio is. Obviously, when I do that, I get 5.000, which tells me that this then, the molecular formula is a factor of 5 of the empirical formula. So I can take that, multiply everything by 5, and my molecular formula would be C5H10O5. There you go. That is how you can use the molar mass to figure out, and the empirical formula to figure out the molecular formula. Now, it turns out that ionic compounds only have empirical formulas. There are no, the reason is for this is that ionic compounds don't actually form molecules. Okay, the nature of attraction between atoms in an ionic compound is due to the charges that the atoms have themselves, and not that there are molecules that have been formed by physical bonds between the atoms. Remember, it's an electrostatic charge that holds those things together, the pluses and minuses hold it all together in a big group, but it's not that there are individual molecules formed in ionic compounds. So therefore, in an ionic compound, hang on here, I'm going to make this light. We don't call any ionic formulas molecular formulas. They are all simply empirical formulas. Okay? So if you see an ionic compound, you know that that is an empirical formula. Okay? Finally, let's look at a little bit with this combustion analysis that I was telling you about. So we've got 115 grams of iron, which we're going to burn in excess oxygen. The result is going to be a solid mass that has 164.5 grams. What is the empirical formula? Now you might look at that and think, well, how in the world can I possibly figure that out? Well, here's what we know. We know that we started with iron and we started with oxygen, okay? And that's going to be O2, of course, because oxygen is a homonuclear diatomic, but it's going to make some compound with Fe and O, okay? I don't know how many atoms of iron, and I don't know how many atoms of oxygen, hence the X and the Y that I'm listing here underneath it. But what do I know? Well, I have been told that the total of what was burned is 164.5 grams. I've also been told that I started with 115 grams of iron. So then I know what has, because of the law of mass conservation, right? I started with 115 grams of iron, I added some amount of oxygen, and the total mass after combusting that or burning that metal oxide was 164.5 grams. So if I want to know how much of this total is oxygen, I'm just going to subtract them, right? 164.5 grams minus 115.0 grams is 49.5 grams. All right, so I have 49.5 grams of oxygen. However, I can't compare substances using grams, can I? So I'm going to go ahead and erase this real quick just to get it out of there. Oops. Okay, and now we are going to go ahead and take these amounts that we have in grams and we're going to turn them into moles. Okay, so I know that if I have 115 grams of iron for every 1 mole of iron, I've got 55.85 grams. That's my molar mass. So that means I have 2.059 moles of iron. Okay, I'm going to do the same thing with my oxygen. I have 49.5 grams of oxygen. Oops, hang on, go back. I'm trying to determine this subscript here. Okay, because I'm determining this subscript, I'm going to use simply O and not O2. That's what I'm figuring out by doing this combustion analysis. I'm not figuring out how many, I already know how many moles I have there. So what I'm trying to figure out is how many atoms of oxygen are present in the final compound. All right, so 49.5 grams of oxygen. For every 1 mole of just O, it's 16.00 grams. And that is 3.09 moles of oxygen. Okay, so then what we're going to do is we're going to compare the ratio of moles of oxygen to iron. Okay, we're always going to take whatever number is bigger and divide it by whatever number is smaller. So the ratio of oxygen to iron is 3.09 over 2.059, which equals 1.5. Okay, so for every 1 oxygen, I have, for every oxygen to, for every 1 iron, for every 1 iron, I have 1.5 oxygens, okay? But I'm not going to write a chemical formula that is Fe1O1.5. That does not make sense, right? So what we're going to do is we're going to multiply this to get whole numbers down here. Now what would we multiply this by to get a whole number? Well, we'd obviously multiply it by 2. And that would give us a molecular formula of Fe2O3. So our, and again, we're not trying to balance the chemical reaction. We could go back and balance the chemical reaction, right? And we would say, oh, I'm going to have 2 of those, I'm going to have 3 of those, and here's my balanced chemical reaction. All we're trying, and you could do that, that's fine, but what we're trying to discern is this molecular formula here. So if we had the amounts of iron and oxygen that they gave us, we would have these ratios that exist, and then these, we would end up with a molecular formula of Fe2O3. An empirical formula of Fe2O3. And that is what you call a combustion analysis. I'm going to do another problem with another combustion analysis, but this is the idea behind these types of problems. So hopefully this is a little bit helpful.